Namaskar, welcome to Sai Economics Point. In today's lecture, we will discuss duality problem in linear programming. Okay, so let's start. Duality is a mathematical process of conversion. Okay, conversion means converting maximization to minimization and minimization to maximization. Every linear programming problems are associated with it and another linear programming problem. Okay, with the same data. The original problem is called the primal and the derived one or the converted one is called the dual problem. Okay, the objective of duality in linear programming is to make the process easier, that is minimization to maximization and maximization to minimization. Okay, and to get many extra information from dual which is not available from the primal, right? For example, let's we take producer's case. Okay, figure A represents isoquants map and figure B, this is the isocost map. Okay, and in figure A, AB is the constant. Okay, and T point, okay, see the T point is the equilibrium point. Okay, and in figure B, T point is the equilibrium point where your isoquant tangents the AB budget line at point T. Okay, at this point, end point is not attainable because of a isoquant constant, and in figure A, M point is not attainable because of a AB constant, right? So optimal leads to both maximization and minimization, and finally your profit maximization equal to cost minimization, right? So in figure A, T point is equal to T point in figure B, that is profit maximization is equal to cost minimization, right? Suppose the objective function is to maximize z equal to p1 x1 plus p2 x2. Okay, where p1 here represents price of good 1 and p2 represents price of good 2. X1 represents quantity of a good 1 and x2 represents quantity of a good 2, and z represents your total profit, and x1 and x2 are the structural variables. Okay, let the constants are suppose there are two constants. Constant 1 is a11 x1 plus a12 x2 is less than equal to b1, and constant 2 is a21 x1 plus a22 x2 is less than equal to b2, and x1 and x2 greater than equal to 0. These are the non-negativity constant. Let's see. A11 represents amount of factor 1 needed to produce, okay, 1 unit of a good 1. Okay, and A12, this represents your amount of factor 1 needed to produce 1 unit of a good 2. Okay, and A11x1, this represents amount of a factor 1 needed to produce x1 amount of a good 1. Okay, and A12x2, this represents amount of a factor 1 needed to produce amount of a good 2. Okay, and a11x1 a plus a12x2, okay, this represents the total amount of a factor 1 needed to produce both goods. Okay, here b1 in constant 1, this represents maximum amount of a factor 1. Okay, similarly a21x1 plus a22x2, okay, represents total amount of a factor 2 needed to produce both goods. Okay, and b2 in constant 2, this represents maximum amount of a factor 2, right? Next we will discuss how to convert this primal problem into a dual one. So there are some steps we have to follow, okay, while converting the primal problem into a dual one. So let's check it. So these are the steps, okay, for primal to dual conversion. Okay, the first step is, first write the standard primal form of the given LPP. Okay, so what is the standard primal form? The standard primal form is all the constants have okay, less than equal sign where the objective function is of maximization form, okay, and all the constants have greater than equal sign where the objective function is of a minimization form, okay, and next is change the objective function of the maximization in the primal into minimization in the dual, okay, and vice versa, right? That is primal maximization, this becomes dual minimization, and primal minimization, this becomes dual maximization, okay, and see inequality signs, this will be become reverse, that is in maximization less than equal sign, this becomes greater than equal sign, and in minimization problem it is given that is greater than equal sign, this becomes less than equal sign, okay, in maximization, okay. Then the next step is if the constant has an equal sign, then replace it by two constants involving the inequalities going in opposite direction, okay. For example, suppose, see, the constant is given as x1 plus 2x2 equal to 4, okay, so there is no greater than equal and less than equal sign, so it is in equality form, so we can convert it into inequalities, that is it can be written as x1 plus 2x2 is less than equal to 4 and greater than equal to 4, okay. uh, So, for standard primal form of the given LPP, if inequalities is in the form of a less than equal, that is in the maximization problem, and we want to convert greater than equal to sign in minimization problem, then just multiply minus 1. Okay, and similarly, if inequalities is in the form of greater than equal to in the minimization problem, and we want to convert it less than equal to sign in the maximization format, then just multiply minus 1, okay, in the whole equation, okay. The next step is say the number of variables in the primal, this will be the number of constants in the dual and vice versa, that means number of a variable, okay, in primal this becomes number of constants, okay, in the dual problem, and number of constants in the primal problem, this becomes number of variables in the dual, that means if there is n number of variables in the primal, then in the dual there will be n number of constants, and if there is m number of constants in the primal, then there will be m number of variables in the dual, okay. The next step is the cost coefficient in objective function of the primal, this will be the right hand side constant of the constant in dual and vice versa, okay. Then next step is row vector of a coefficient in objective function of a primal, this becomes column vector of a constants in dual, and column vector of a constants in primal problem, this becomes row vector, okay, that means transposition of a matrix, okay. And the next step is the number of structural or you can say decision variables in the primal problem, this becomes the number of slack variables in the dual, okay. And number of slack and surplus variable in the primal problem, this becomes the number of decision or structural variables in the dual, right. So and next step is non-negativity constant is common to both primal and dual, so there is a no change in the non-negativity constant, it will remain same in both primal and dual, right. Next important step is if there is unrestricted variable, okay, then it is replaced by the difference of two non-negative variables. For example, if xn is a unrestricted variable in a problem, then it is replaced by x1 equal to x1 days minus xn double days, right. So these are the important steps while conversion of a primal problem into dual problem, okay. Let's see how we can convert the primal problem into a dual one. So this is the primal problem. Now we want to convert this problem into a dual one, okay. If you write the primal objective function into matrix notation, then this will become z equal to p1 p2 into x1 x2, okay, and structural constant this becomes a into x, this is less than equal to b, where a represents matrix of a coefficient and x represents your matrix of a variables and b represents your matrix of a constant. Okay, now we will convert this primal problem into an dual one. Okay, so it's and we know we have first we will change the objective function of maximization in the primal into minimization. So the objective becomes to minimize, okay, c equal to, here it becomes b1 c1 plus b2 c2. Okay, where here c1 represents price of factor 1, okay, and c2 represents price of a factor 2, and your c represents total cost of a production. Okay, next one, as you know, the number of variables in the primal, this will become the number of constants in the dual. So in the primal problem there are two variables, that is x1 and x2. Okay, so in the dual problem there are two constants, that is constant number 1 is a11 c1 plus a21 c1 is greater than equal to p1, and constant number 2 is a12 c1 plus a22 c2 is greater than equal to p2. Okay, the next step is cost coefficient in objective function of the primal. This will be RHS constant of the constant in dual. Okay, and vice versa, that is p1 p2 in the objective function, this becomes your RHS constant of the constant in the dual. Okay, so next is a row vector of a coefficient in objective function of a primal becomes column vector of a constants in the dual, and column vector of constants in primal becomes row vector constant in dual. That means transposition of a matrix. Okay, so as you can see, this a11 a12 becomes here a11 a12. That means this row becomes column, and a21 a22 row becomes column here a21 a22. Okay, and coefficient row vector in objective function becomes column vector in right hand side constant in dual. Okay, and b1 b2, that is column vector in RHS constant in the primal, becomes coefficient row vector in objective function in dual. Okay.